Well, last time we didn't get a chance to finish all the problems I had planned. So I thought, let's pick up right there. So here's a problem. A sales representative is planning a trip to visit each of 5 cities and return home. No city will be visited twice. How many different trips are possible if, and there's 2 scenarios, so we'll work through A first. If A, the sales representative will use their own car for the trip, or take flights for all legs of the journey. All right, so let's think about this. We have our sales rep. They live somewhere that maybe will represent their hometown by a circle, and then there's going to be 5 cities that they're supposed to visit. Now, the thing is, what can we change? Like, what's in our control? When we count how many, it's like, well, what's allowed to be altered? So what do we get to pick in this problem? Yeah, there's 2 things. One of them is the order of the cities that we visit. What's the other thing? Yeah. So it's the mode here. So this is their mode of transit, or the method that they'll be using. And then there's the order. So we have to account for both of those. All right, so let's talk about the order of the cities. So we see that there are 5 cities they're going to visit, then they're going to return home. So we can think of filling in like, okay, my itinerary is I have 5 slots. I'm going to put a city in each slot. So if we're building up this itinerary, we can do it from, say, left to right. Say, okay, how many choices do we have for the first city that we're going to visit? Well, there's 5 cities, and so that's 5 choices. How many options do we have for the second city that we're going to visit? 4. What about for the third city? 3. For the fourth city? 2. And for the last city, there's no choices at all. We just have to go with whichever city we didn't pick. All right, so what do we do with these numbers 5, 4, 3, 2, 1? Multiply. Okay, so the order of travel, that's going to give us 5 times 4 times 3 times 2 times 1. We'll talk about what these kinds of numbers are in just a minute. That turns out to be 120. All right, so how many different methods of travel, or modes of transportation, do we have to pick from? 2. So now we combine the order plus the mode. What's our final answer? Is it 122? No. It's 240. And I like to think of it, if you go back to one of the things we talked about last time, there's an and sort of thing going on. I have to pick a way I'm going to travel, and I have to pick an order I'm going to travel. And when you think of words in problems in terms of counting, ands, those are multiplication type words. Okay, so part A, 240. Cool. Part B. The sales representative will either take a train or a flight for each leg of the journey. So now, it's slightly different. What's changed between the 2 things? Because we have 2 things, so like the order they visit the cities, the mode of transportation. The mode has changed. The order is still, we still have that same 5 times 4 times 3 times 2 times 1. All right, so if we think about it, we have to say, to think of multiplication, again, the ways that we're going to move ourselves from place to place, and times that by the order that we visit the city. Or visit the cities, plural. Well, this stays the same, 120. What will this be? Now, previously, we had to make a commitment for the entire trip. So it was one choice we made at the very start, and we stuck with it for the whole trip. Here, we don't have to be so rigid. We say, oh, I can make a choice every time I make a trip. So, how many different trips are we going to make in total? Let's maybe answer that question. We're visiting 5 cities. How many trips do we make? And why is the answer not 5? Because there's something else we do. We visit 5 cities and return home. So there's 6. So, even if we did something as simple as they went from to A to B to C to D to E and back again, that's 6 legs of the trip. Okay, so for each leg of the trip, we have 2 different options. So 6 parts of our trip, 2 options for each part. How many different counts do we have? What's the contribution for our mode of transit from our place to place? It'll be 2 times 2 times 2 times 2 times 2 times 2. Right, there's 6 legs. Each one gets 2. But there's an easier way for us to write this down. What's another way to write down 2 times 2 times 2 times 2 times 2 times 2? 2 to the 6. Okay, so this is one I probably can't do in my head. 2 to the 6, that's not too bad. That's 64. So 64 times 120. And, there's a reason they made calculators, right? Take 64 times 120, and we get a syntax error because I probably didn't clear everything. Clear. 64 times 120 equal. Okay, my calculator is not working today, so, there we go. It's one of these things that you have to figure out how your calculator works. Harder than you think. 7,680. There we go. Wow. Okay. So you can imagine that that's a lot of options. I will say there's a famous problem in mathematics. It's called the traveling salesman problem. And it's been around for, 100 years or more. And it's the problem of you have somebody who wants to travel around and they want to visit the cities, again, in order. And so the challenge becomes, you actually know the distance between each pair of cities, and you want to say, the salesperson can't afford a lot of gas, for instance. So they want to find the shortest total distance. And that's an incredibly hard problem. I think they it used to be they'd have a hard time doing just 20 or 30 cities. Now they can do a couple hundred, maybe a few thousand, but it's a well-studied problem. All right, any questions on this one? Hangover from last time. Okay, we will see, as I said, these numbers very shortly. So, paper's all sticking together. A quick thought for the day from Albert Einstein. And one of the things he said, of course, he said a lot of things. He also didn't say a lot of things. It's one of those things that once you become famous enough, people like to attribute quotes to you because they'll think it carries more gravitas. Well, what was something Albert said? Any fool can know. The point is to understand. And one of the things that this comes back to is that there's different levels of knowledge. And sometimes, you might think of it as like it's like a light switch. You either know something or you don't know something. But that's not quite right. You can say, well, I know the name of it, or I've seen the concepts before, or I can apply the concepts, and so forth and so on. But one of the deepest levels of understanding is to say, I know why it works, and I know how to apply it. So you don't just want to go for surface level understanding. Make sure you fully understand what's going on. Don't accept less than what you deserve. All right, what's our goals for today? Well, we're going to talk about permutations and combinations. These are particular things that get counted, and they frequently show up. Essentially, you can think of the difference between the two is whether order matters or not. So for permutations, we're talking about taking a group of n objects, we pick r of them out, and we rank them. Put them in a list of some sort. For combinations, we can think of that more as a collections. I have a group of n objects, and I pick r of them out, and I just say, look, you're all together in a set. Sets, order doesn't matter. So it's just a matter of picking them out. So that's what we're going to talk about. We'll talk about how you compute these, and then we'll also talk about the various ways to notate these. All right, so let's start. First off, you may have noticed that there were some very emphatic letters here. They were like, it wasn't just like an N. It was, no, like that exclamation mark. Well, actually, the exclamation mark means something slightly different. So this is what's known as factorial. So we should have this for reference. So n factorial means the following. You're going to multiply the first n numbers. So n times n minus 1 times n minus 2, and you keep multiplying down till you get to 1. And because this shows up so frequently in lots of areas in mathematics, they said we want a shorthand way to denote this, so we use the factorial. And so 1 factorial is just 1, because there's only one number. 2 factorial is 2 times 1. 3 factorial, 3 times 2 times 1, and so forth and so on. Now, one of the things that does happen with factorials is that they grow quickly. Oh, sure, the first couple seem harmless enough, but 8 factorial, that's 40,320. 10 factorial is like 3.6 million. So it grows very fast. So it's one of the things you have to be careful about. Now there's this weird thing, which you might notice is that we actually didn't start by putting down 1 factorial, we put down 0 factorial equals 1. And you might say, well, wait a second, that doesn't seem right. But then you have to say, why did they do it? Well, if you've ever done any programming, a programmer would look at this and say, oh, this is notation for if you see an exclamation mark with equal, that's another way of saying for a computer not equals, and 0 does not equal 1. Okay, but we're not programmers. That's not us. So let's instead think about it in a different way. I said n factorial is you're multiplying together n numbers. And they happen to be the first n natural numbers. So if we were doing 0 factorial, how many numbers should we be multiplying together? You multiply 0 numbers. Now the question is, what does it mean to multiply no numbers? What do you have? Before we answer that, let's ask a different question. Instead of multiplication, suppose I have addition. And I said, oh, I don't have any numbers added up at all. There's nothing there. What do you have? What's your answer? 0. Like everyone agrees with addition. They're like, I agree. If you add nothing up, you have 0. Well, what's special about 0? 0 has a special property when it comes to addition. The special property has, if you add 0 to anything, it doesn't change that anything. Now let's switch to multiplication. Is there a special number for multiplication? In other words, if you multiply something, that special number times anything, you get the anything back. 1. And so the idea here is just in the same idea of adding nothing gives you 0, multiplying nothing gives you 1, because nothing's changed. So the default is 1. It's called the multiplicative identity. Why does it show up? Well, what does n factorial count? Counts the number of ways to arrange n objects into a list. Another way that you often hear about this is permutations, and we're going to talk about that in just a second. Permutations are just rearrangements. So you have n things, sort them into a list of n things. So let's go into permutations. This is the number of ways to arrange r distinct objects into a list out of n possible objects. So I have a pool. There's a collection of n objects, and I'm going to select r of them out. So it's like I pick the first one, I pick the second one, I pick the third one, up until I pick the rth one. So how many ways are there to do that? Well, I say, okay, I pick the first one, and I have n objects. So there's n ways for me to pick the first one. And then I say, okay, now I pick the second one. Well, I've already picked out one object, so that means I have one less. So that's my n minus 1. Now, when I pick out the third object, how many options will I have? So n for picking out the first one, n minus 1 for picking out the second. How many options will I have when I pick out the third? N minus 2. And the pattern continues, dot, dot, dot. If you ever see dot, dot, dot in mathematics, that's the shorthand way of saying, and the pattern continues. Up until you pick out here, this is you pick the rth object. Now you say, well, wait, why is it r minus 1? Well, just in the same way, at the beginning when we picked out the first object, it was really n minus 0. The second object was n minus 1. So the rth object is n minus r minus 1. All right, so that's the idea. All right, great. But that seems like a lot of stuff to write down. We'd like to make it a little bit simpler here. And we say, okay, well, it's feeling like a factorial. Like a factorial starts at n, and then it goes down, and then it keeps going down. The problem is it doesn't go down to 1. It sort of stops short. So we say, okay, we'll never stop, never stopping. Let's have it go all the way down to 1. So we're going to add some terms on the end. But I need to balance that out. So what we can do is we can divide by the same things that we added upstairs, we put downstairs, so that just doing cancellation gives us what we had before. But now the upstairs, we say, aha, factorial. And the downstairs, aha, also factorial. And so we see that the number of ways is n factorial over n minus r factorial. And we write this in the book's notation. This is P for permutation, nr. All right. So the first subscript on the left, the total number of objects. Subscript on the right, that represents how many you're picking out. Let's see. Let's test ourselves. What can we say n, p, n? What would that be? You have n objects. You pick n of them out in order. What should that be? We can either reason it or we can apply the formula. Does anyone have a reasoned answer for what it should be? Let's see what the formula says. According to the formula, you can say, okay, this first term goes there and there, while the second term goes into that slot there. So we say, all right, well, this is n factorial over n minus n factorial. N minus n factorial, n minus n, also known as 0 factorial. But what is 0 factorial? It's 1. So you're left with n factorial. And no reasonable person, by the way, will replace all their n factorials by this notation. But we can write that down. All right, good. So that's permutations. Any questions on that one? All right, the most important thing is for permutation, order matters. So that's why I said you pick a first one, you pick a second one, so forth and so on. Now we go to combinations. And in combinations, it says, hey, order is not important. So again, you have a pool of objects, n objects, and now we're going to pick R of them out, but we don't care the order that we picked them out. Just at the end of the process, we have R cards. All right. So, our question, how many ways can this be done? Now, let's think about it in a slightly different approach, is to say, one thing we can do is let's just look at NPR, the number of permutations. We did that before. Now, my question, how does the number of permutations relate to the number of combinations? What do you need to do? You need to forget the order. So, let me do a quick example here. I hope this is quick. Suppose we do n equals 4, r equals 2. So when I say 4, I'll just use the 1, 2, 3, 4. So I want to pick 2 objects out of a group of 4 objects. So one thing I can do is I can say, well, let me list all the ways I can just grab 2 objects where I grab them in order. So I could do 1, 2, 1, 3, 1, 4. I could pick 2, 1, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 4, 1, 4, 2, and 4, 3. So those are all 12 ways that I could grab something first and then grab something second. Now the thing is, I want to forget the order. And as we look at this, we say, oh, wait a second. Some things show up twice if we're forgetting orders. Like this 1, 2 matches with this 2, 1. What else matches? Yeah, like the 1, 3 will match with the 3, 1. And you can go through and do this very systematically. Whoops, I wrote down 3, 3. That's not right. I should have written down 3, 4. My apologies. But you can go through and just systematically pair things up. And so you say, oh, okay, well, what's happening? Well, one way you can think of it is you could say, if I just grab all the permutations, then what's going to end up happening is I'm going to overcount the combinations. Because sure, we'll have picked out all ways to pick out our objects, but I'll have counted them too often. So what we want to do is to say, okay, let's have an idea. Let's count something we know how to count, and then we'll fix our counting error. So we're going to have a correction. So this term downstairs, this fixes our overcounting. Now you might say, okay, well, what do I mean by overcounting? Well, if I have R objects, how many ways could I have picked them out? How many different orders could I have picked them out in? Well, I could have said R times R minus 1 times R minus 2 all the way down to 1. So there's R factorial ways that could have been arranged. So that's why you see 2 factorial is 2. There's 2 ways I could have picked things out. So we end up with the formula for our number of ways to pick things out is n factorial r factorial over n minus r factorial. Oftentimes people do this using these long parentheses, n over r, and I forgot to write down the other notation is similar to the c, and then you just put the n and the r. And when you're applying this, just as before, say, okay, where does the n go? Well, the n will go into 2 slots. And then the r also will now go into 2 locations. Same as before, but now we have this extra term. Okay, well, let's try out some computations. Find the following. 20 P3. So what is 20 P3? Well, we can write down the formula. So we say, okay, this is our n. That goes upstairs. Downstairs, we would have 20 minus 3 factorial. So this becomes 20 factorial over 17 factorial. What can we do? Well, one thing we can do is see if our calculator has a factorial button. Mine actually doesn't. Not all scientific calculators do. Some financial calculators do, some scientific calculators do. So you'll have to check. But okay, so I don't have a button that says factorial. Does that mean we give up? Or do we leave our answer like this? No, we want to go and get to a number. So let's think about what we can do. So one thing we can do is we can say, well, which one of these is larger? 20. Okay, so I'll start by writing down 20 factorial. That's 20 times 19 times 18 times what's next? 17. And what comes after that? Well, 16, 15, 14. So what I can do is I can replace 20 factorial by 20 times 19 times 18 times 17 factorial. In other words, I can sort of pull off the start of the factorial up until the point I need. And I stop at 17 factorial. The reason I stop at 17 factorial is what's downstairs. Well, 17 factorial. Now what can you do? Cancellation. Nice. So instead of having to multiply a lot of numbers, we only have to multiply a couple of numbers. So now it becomes a problem we can do without a fancy calculator. We can just type 20 times 19 times 18, and out comes 6,840. All right, so that's our first number, 20P3. Now what about 20C3, the combinations? Sometimes I'll read this out loud as 20 choose 3. I don't know if people read this out loud as 20 permute 3, but definitely people read this as 20 choose 3. So 20 objects, choose 3 of them. Well, we have the formula, and it looks very similar. So it's 20 factorial. The only new thing is we have this extra r factorial. So, okay, we plug it in. So we say, all right, well, that's really 20 factorial over 3 factorial, 17 factorial. But we can do what we just did before and say, you know, this 20 factorial over 17 factorial, that's 20 times 19 times 18. Now 3 factorial, okay, that's small enough I can multiply that out. Now, a question. Will this always be a whole number? I'll put it as a question. If I ask you, like, 75 choose 31, will it always be a whole number? Or might there ever be a fraction? And the answer is, it's always a whole number. And why is it a whole number? Because it's counting something. When we count things, you can't say, oh, a fraction of a thing happened. It's just, when we count, we'll say, okay, how many times does something happen? 1, 2, 3. So it's always going to be a whole number. So if you do a computation and you end up with a fraction, something in your computation is wrong. So instead of putting a question mark, we can turn this into an exclamation mark. So just on a side note. Now the good news is we already took 20 times 19 times 18, and 3 times 2 times 1, we can do that in our head. That's 6. So we just take our previous answer and divide by 6, and so we get 1,140. So a lot fewer combinations than permutations, but that should not surprise us. All right, the last one, n factorial divided by n minus 4 factorial. What can we do? Well, we can do what we were doing at the very beginning, which is to say, oh, which one's bigger? Let's start pulling terms off. So we can say, okay, I'll start upstairs, pull off an n, and how far do I go? When do I stop? Or do I ever stop? It's just an infinite assignment. I claim you stop now, because you've reached the point where the other one starts. So you say, okay, pull off the first term, pull off the second term, pull off the third term, pull off the fourth term, and then the rest of it is its own factorial. And those cancel. So we end up with n times n minus 1 times n minus 2 times n minus 3. I will say, this one was inspired because I did take a peek at the homework. It's nice to look at the homework and know what's coming. And they said, well, let's have you do one of these. And I said, oh, okay. But that one, they said, we'll have you do n factorial divided by n minus 12 factorial, at least in my version of the homework. And so you had to keep writing n minus 1, n minus 2, n minus 3, and keep going all the way up to n minus 11. I hope your version is much nicer to you. But it's not hard once you understand what's going on. It's just tedious. All right. There are 9 people running a race. In how many ways can gold, silver, bronze be awarded to the people? So ultimately, you should sort of start thinking, does order matter or does order not matter? So we're thinking of permutations versus combinations. Does order matter here? Yeah. It's very different getting a gold than it is a silver than it is a bronze. Gold people, very happy people. Silver people, very sad people. Bronze, also very happy people. Somehow being second is the worst thing for your mental health. You might say, well, wait, why is a bronze person happy? Well, they may have been fourth, and then they would have gotten nothing. So they're pretty happy they got something. So, all right. It's all perspective, I suppose. Okay, so these aren't meant to be long. We're not going to fill up the page. If we use the language, what are we doing here? This is a permute problem, So we have sort of two boxes here. On the left, why did I write 9? Sorry. P for permute, not backwards P for okay, 4. So on the left, that's the total number of things. On the right, that's how many you have to pick out and rank or list in some order. What goes in the left? The 9. There's 9 people in the race. What goes in the right? 3. There's 3 positions we have to fill up and sort them in order, 1, 2, 3. So that's one notation, but we want you to go a little bit further. Okay, so that's 9 factorial over 9 minus 3 factorial, which again is 9 times 8 times 7 times 6 factorial over 6 factorial. And I've made so many errors. I want to guess this is 504, but I'm not going to guess. We'll take 9 times 8 times 7 to get 504. Okay, good. All right. Now, one of people's favorite topics, committees. I'll tell you, if you ask a faculty member, well, at least they're the people I know a lot about, what they hate the most about their jobs, they'll usually say committee work. Ugh. All right. So there's a committee with 10 people, a group of people. How many ways can a 4-person subcommittee be chosen? Okay, so let's deal with this one first. We have a 4-person smaller collection. Is this permutation, combination? Which one? Combination. Because it's just a subcommittee, it's just like I have a group, it's like a set. I'm making a smaller set. So right now, there's nothing here that says order is important. Order is not important right now. So we say, okay, so this is 10 choose 4 or 10 choose 4, however you like to notate that. So that's 10 factorial over 4 factorial, 10 minus 4 factorial, which will take us a second here. 10 times 9 times 8 times 7 times 6 factorial. Then there's a 6 factorial downstairs, that 10 minus 4 factorial. The 4 times 3 times 2 times 1, that's our 4 factorial. Okay, the 6 factorials cancel, and these are numbers I don't want to try to do in my head. I mean, it's fun to think that the answer is going to be something like 210, and I think that's what it is, but there's no points awarded for doing things in your head. There's points awarded for getting the right answer. So we get, it is 210. Nice. By the way, in case you're wondering, how does he do that? Well, you can do things such as notice like, oh, hey, what is 4 times 2? It's 8. So I can combine the 4 and the 2 and cancel with the 8. And I say, oh, there's a 3, 9, that has 2 3s, so I'll cancel out there. No terms left downstairs, and then 10 times 3 times 7. That's something you can do. 3 times 7 is 21, then 10 adds a 0. So it wasn't like, it's like, I don't have a built-in calculator. At least not a very good one. Okay, the second question. How many ways can a chair, vice chair, secretary, and treasurer be chosen from among the members of the committee? So let's actually make sure we have this right. So there's a chair, so that's position 1, a vice chair, position 2, a secretary is position 3, and there's a treasurer is position 4. So there's 4 positions. We have to choose them from among the members of the committee. What do we do? What do we do? So, does order matter or does it not matter? Order matters, right? Now, to say order matters, you can just say, look, somehow we're distinguishing things. If you don't like the phrase order matters, it's like, what do you mean? How do you order a president versus a treasurer? You can think of it as, is it important to distinguish them? And here it is. It's different if you swap roles. That's a different assignment. So, what would this be in our notation? Combination or permutation? Permutation. So this is 10p4, which is 10 factorial over 10 minus 4 factorial. Okay, so 10 times 9 times 8 times 7 times 6 factorial over 6 factorial. And it's going to be something. I won't do this in my head. I'm getting old. By the way, you could just take the previous answer and multiply it by 24. 5,040. Cool. We must have done this before today. All right. Cool, cool, cool. So, a few more. We have time for one or two more. A catering service offers a selection. So there's this event going on. This happens a lot. And they have like a big menu, and you're going to pick a sub-menu out of it. They have 8 appetizers that they could make. They have 12 different main courses. That's pretty good. Nice selection there. And 6 different desserts. Now, your event, you don't want the full menu. You just want to pick some things out that are appropriate. Maybe like you're at an event and you have to say, there's a lot of people who have certain allergies or whatnot, so you have to narrow things down. And he says, okay, so this particular event is going to have 5 appetizers, a choice of 3 main courses, and 4 desserts. So then how many different alternatives will there be? If you want, you can almost think of alternatives as menus, right? You're picking things that are going to be on the menu. So how do we figure this out? Okay, so combinations versus permutations. If we were thinking this as a menu, well, we have our appetizers, call these the apps, our main courses, which I guess we'll call our mains, and our desserts, which I don't know a good shorthand for that, we'll call it desserts. So we're filling up our menu. And now, let's think about each part of our menu. How many different ways can we pick out the appetizers? Permutations, combinations, what do we have? Well, there's a total of 8 appetizers, and we're going to pick 5 of them out. So I'm only picking out 5 things that are going to go into our apps. So how many ways are there to do that? Does order matter when I'm listing the appetizers on what's available? No. So that's a combination thing. So just figuring out what goes into the appetizers, we say, this is a combinations thing. We can write this as, I'm going to write it using this 8 choose 5 notation. It's a notation I'm more familiar with. Use the notation you're more familiar with. But be ready to recognize it if they offer you a different variation. Now, there's a lot of main courses that could be served, but you're going to make it more simple so people won't have to think so hard. There is a strange thing that happens. If you have too many choices, you end up being less happy with the choice you made. The problem is if you have too many options, you're like, I could have had something better. You always question your answer. But, if you go into a store and you have 2 types of toilet paper, you're like, okay, that makes my decision easy. So sometimes too many options is a bad thing. And in that, you say, look, we're only going to have 3 different main courses. So, how many ways are there for us to do that? There's 12 that we could pick. We're going to choose 3 of them. So we're choosing 12. Sorry, there's 12. We're going to choose 3. For desserts, we have a sweet tooth. We don't want to limit ourselves too much with desserts. So there's going to be 4 desserts out of the 6 possible available. And so we say, okay, there's 6 desserts. We're going to choose 4 of them. What do we do with these numbers? We multiply. So we're going to take 8, choose 5, 12, choose 3, 6, choose 4. So this is going to give us a lot of things here. 8 factorial, 5 factorial, 3 factorial, 12 factorial. There's going to be a 9 factorial, 3 factorial, 6 factorial, 4 factorial, 2 factorial. Whoops. And let's see if we can't simplify things. So for the 8, we can write that as 8 times 7 times 6 times 5 factorial. And then we can cancel off a 5 factorial. 12 is 9, sorry, got ahead of myself. 12 times 10 times 11 times 9 factorial. We can cancel off a 9 factorial. All right. 6 factorial is 6 times 5 times 4 factorial. So we can cancel off a 4 factorial. That leaves us upstairs with 8 times 7 times 6 times 12. Why did I do 11 times 10? That's so weird. Sometimes my brain doesn't work right. Okay, downstairs we have 3 factorial, which is 6. Another 3 factorial, which is 6. And a 2 factorial, which is 2. And, well, 6 times 2 is 12. Might as well save ourselves some work. The 6 cancels. So now we just have to multiply these numbers together. And then we'll be done. 8 times 7 times 11 times 10 times 6 times 5 gives us 184,800 different menus. That's a lot. That's why it takes months and months to plan a wedding. Think of all the menus that you have to consider and go over. No, that's not why. But certainly, there's many things that could happen. Maybe one more quick one. We won't do the full computation, but we'll just write down the answers in terms of C's and P's. An office supply store receives a shipment of 24 printers, including 5 that are defective. 3 of the printers are shipped to a local school. How many selections of the printers to be shipped can be made? So, how many printers are there? There's 24. How many are being shipped? There's 3 being shipped. So, I take 24, I choose 3. What's the answer? 24, choose 3. All right, that's part A. How many of the selections of the printers to be shipped will include no defective printers? How do we change the answer for part A to get the answer to part B? So part A says, I don't care whether you're defective or not. I have 24 printers. I'm picking 3. Off they go. Yeah, so now we say, look, instead of having the pool of all 24 printers, we're going to cut our pool a little bit, a smaller pool. Now there's just 19 printers. And we say, okay, it's a smaller pool, but we're still shipping the same number. It's still 19, choose 3. And so that's how many options we have that will have no defective printers. And this will lead to something, by the way. We're going to lead up to probability. That's going to be one of our our big last set of topics. And it turns out for a lot of probability is counting. So it's good to be good at counting if you want to be good at probability. All right, that's it for today. And we'll pick up again next time.